Hello and welcome to the latest little tidbit. This time, why there is a speed limit in the universe and why that speed limit is the speed of light. So we're going to run through a few stages as we get there. First off, Einstein's theory of relativity puts a speed limit on the universe. Specifically, that speed limit is the speed of light in a vacuum, given the variable c. So why would that be a speed limit? It's because the theory of relativity is a lot more than just that formula, E equals mc squared. In fact, E equals mc squared is a footnote that got expanded into an appendix after Hiroshima and Nagasaki. So in a 200 or so page document, when you buy it in the printed edition, we started with a footnote. That printed edition, like I said, I bought a copy. The theory of relativity, at least the earlier editions, are now public domain and can be downloaded legally and for free from Project Gutenberg if you're interested in reading it. So the speed of light was measured experimentally and rejected for being way too fast because it was so much faster than anything else anyone had ever observed. Then James Clerk Maxwell compiled all the equations describing electricity and magnetism, and he recognized that when an electric field changes, it produces a magnetic field. And when a magnetic field changes, it produces an electric field. So it is possible for changing electric and magnetic fields to keep each other going and be self-propagating. In that case, he calculated the speed of that wave. This is the calculation he came up with. That constant epsilon with a subscript 0 measures how easily electric fields penetrate the vacuum. The constant mu with the subscript 0 measures how easily magnetic fields penetrate the vacuum. These two together produce that speed of light, and that was consistent with what had already been experimentally measured. So most people were blown away by this calculation because it finally explained what light was. So not only was the earlier experimental number actually valid despite being insanely high, it was valid and consistent with theory. That's the one that said, okay, this light itself is an electromagnetic wave. It is very important to note that both epsilon 0 and mu 0 are physical properties of the universe itself. Why that's important, we're going to get to. So when we're studying motion of any object in a lab, we use both position and time. We measure position relative to the room or something in the room that we are in, ignoring Earth's motion around the sun, ignoring the sun's motion in the galaxy, ignoring the galaxy's motion in the universe, etc. We measure time relative to when we start our stopwatch. These work well enough unless your equipment is sensitive enough to detect the Coriolis force of the Earth rotating on its axis. This analysis is based on the changes in these variables, not some absolute motion. So we don't have to say, here is the zero position for the universe. We don't have to start time with the Big Bang. We can start it within that room. If you were to put your lab in a moving train, as Einstein's thought experiments did when he was explaining things in the theory of relativity, someone on the train will measure different numbers for the position than someone on a bench looking in the train windows as it moves past. Both observers will see consistent physics and make accurate predictions. Before Einstein, they would agree on the time, or at least we thought they would agree on the time, but not the position. And we'll talk about why that is in a moment. Einstein was the one who looked at Maxwell's equation and didn't say, wow, that's what light is. He said, wait a minute. Epsilon 0 and mu 0 are the same for all observers. They're physical properties of the universe. So therefore, the speed of light must be the same for all observers, no matter what their relative motion is. So if a person is riding a train and they turn on a flashlight, they can measure the speed of light as that light goes from one side of the train car to the other. The person on the train and the person on the bench will measure the same speed for that photon of light, even though they measure different changes in position. So these two observers, one on and one off the train, measure the same speed for light. They disagree on the change in position. How? The person on the train says that light went from one end of the train car to the other, so the total change in position is just the size of the train car. The person on the bench will measure the length of that train car plus the distance traveled by the train itself. Now, speed is a ratio of position and time. So these two would agree on the ratio, but not the numerator. That means you cannot agree on the denominator. We must have some sort of equivalent fraction situation here. We could have one person saying it's 5/2 and the other saying it's 10/4. They will agree on the overall ratio, but not on the numerators, not on the denominators. Different people must therefore measure time at different rates, depending on how they are moving relative to each other. Hence the theory of relativity. That's actually why the theory was given that name. It's about how they are moving relative to each other. So how does this create a speed limit for the universe? Imagine two spaceships moving in opposite directions, each at 3/4 of the speed of light. Your instinct says that each ship would say the other is flying away at 6/4 or 3/2 of the speed of light. Well, that's more than the speed of light. Now, each ship turns on headlights. They will both say light is faster than the other ship. But light moves at the speed of light. Light moves at c. Therefore, they must say the other ship is moving at less than the speed of light. No matter how much thrust either ship uses, the light from its headlights will always be faster and will always be moving at c. Well, what's the math behind this limit? The energy of an object with mass m and speed v is given by this equation. Seems a little weird. Note that when v equals 0, so when it's not moving, we get E equals mc squared. That's that famous footnote. If we subtract mc squared from this equation, what we'd have left is the kinetic energy. Doesn't look like that 1/2 mv squared that we saw in Newton's day, but if you know calculus, you could do a Taylor expansion and approximate any equation with an infinitely long polynomial. The first term in that polynomial is 1/2 mv squared, and the next few terms are divided by c squared, c to the 4th, c to the 6th, which is why Newton's equation seems to work really well until we are at significant proportions of the speed of light. This equation also has a vertical asymptote at v equals c, meaning the energy will climb to infinity as v gets close to c. Remember, when we're speeding things up, we don't add speed. We don't add 10 meters per second. We add kinetic energy. There's no limit to how much kinetic energy we add to this. We'll keep adding energy and energy and energy, but the speed of light will always be less, or the speed of that object, will always be less than c. That's where the speed limit comes in. Energy goes to infinity as v approaches c. So no finite amount of energy will get your speed up to the speed of light. So I hope that helps make this clear.